Hello, and welcome to this presentation on coupled inductor confusion. In this short presentation, we want to go over the basics of what a coupled inductor is and how they're used in power electronics. First, I want to talk about the schematic symbols, and then about the different types of magnetics we refer to as coupled inductors, and finally back to the standardized symbols that are used to represent them. In your typical schematic, we see this symbol used to represent a transformer. There are two wavy lines to represent the windings, and usually a couple of lines to represent the core. Polarity dots may or may not be present, depending on if polarity is important in the circuit. Use this symbol for common mode chokes, sometimes called current compensated chokes. It just looks like the transformer on its side, but it's not a transformer. We use this symbol for flyback transformer, which looks just like the transformer, but with one polarity dot in a different place. We'll discuss later if this really is a transformer. And lastly, we use this one for coupled inductors. Looks like the common mode choke with the polarity dots in a different place. Or is it a flyback transformer on its side? Three of these are coupled inductors, and you can only tell the difference from the usage context. It's hard to see the difference. Let's start out by defining what an inductor is and also what a choke and a reactor are, because these terms are commonly interchanged. From the schematic, you can't really tell because they all look the same. An inductor is a two-terminal magnetic device that has the property of inductance, which impedes the change in the flow of current. They range from extremely small to very large and come in many different shapes. They're basically a coil of conductor, usually wire, normally with a core to increase the inductance per volume. When current flows through the coil, a potential voltage develops across the terminals and opposes the current, Lenz's law. The energy is stored temporarily in the magnetic field. The inductor resists change in current, so mechanically it acts a lot like a flywheel. It takes a bit of energy to get it going, and once it's going, it doesn't want to stop. And the inductor works exactly the same way. Initially, the current ramps up because it's resisting the change in current. Once the current is flowing, it's fine, but when you remove the driving voltage, the current wants to keep flowing, resisting that as well. Unlike a capacitor, which can hold energy for a long time, the inductor must release its stored energy if the applied voltage is removed. The collapsing magnetic field creates a rising voltage until current flows somewhere, a spark if necessary. The term choke is often used for filter inductors that have a large DC bias, like output chokes. Obviously, the term is very interchangeable with inductor. The term reactor is most often used with AC-only inductors. We typically don't see that in switching power supplies. Let's make sure we're clear on our definitions. An inductor, as we've just defined in the previous slide, is a magnetic device that impedes the flow of electric current by storing and releasing energy from its magnetic field. A coupled inductor, on the other hand, is an inductor with two or more windings on the same core, which takes advantage of the magnetic coupling to influence the behavior of each winding on the other. A transformer, on the other hand, is a magnetic device that transfers energy instantaneously through its magnetic field. It typically changes the voltage or current, and it provides galvanic isolation. By definition, a coupled inductor is an inductor, not a transformer. By function and by design, they work on different principles. One stores energy, the other transfers energy. The schematics may look the same, but they are not interchangeable. Here is our first coupled inductor, the common mode choke, sometimes called the current compensated choke. What you have are two windings that are wound in the same direction on the core. In this case, one traverses to the left and the other to the right, but the direction through the core is the same. Flux created from common mode currents goes in the same direction, so it adds in the core and is presented with a large impedance to impede unwanted signals like noise. Flux created from differential currents cancel in the core because they go in opposite directions. This is important because in this type of inductor, you want to use high permeability core to get the most inductance for the fewest number of turns. The trouble with those materials is they tend to be sensitive to DC bias. Since the differential currents cancel, this is not a problem. The trick to operate at high frequencies, aside from using a high frequency material, is to keep the winding self-capacitance as low as possible, and to do that you want to have the fewest number of turns nicely spaced. You want tight coupling so that the differential currents completely cancel and you get the most advantage from the common mode currents going in the same direction. Here is a variation where we have the simplest coupled inductor, a toroid, ferrite bead, or snap-on type ferrite. When you run a cable or more than 2 wires through one of these, you have effectively created a common mode inductor that's used to attenuate unwanted signals. We've all seen these on USB and video cables, those little bulges near the connectors. The inductance is fairly low, and the cores are deliberately lossy. The attenuation mechanism is to convert high frequency to noise to heat. Adding more turns increases the inductance, which gives more attenuation, making it more effective at lower frequencies. This is exactly what you want in a lot of low voltage signaling applications like Ethernet or HDMI video signals. These often have toroids that look exactly like this, where there are multiple signal lines all wound together around the core to provide attenuation to common mode currents. Here again, all windings influence each other and then give you the attenuation that you want. In high voltage applications, you just separate the windings from each other. They're still going in the same direction around the core as you've seen earlier. You can see why polarity dots, which aid in proper connection, are important. Here you have a gap between the windings to meet safety and spacing requirements between the high voltage lines. There's usually some kind of plastic spacer to mechanically secure the spacing, which has to be guaranteed. You can have the windings on 2 separate core legs, or you can have it split on 2 different sections of a bobbin. In all cases, it's a common mode inductor that's doing the same function of attenuating common mode currents and not affected by differential currents. Here's another advantage of common mode inductors used in differential signaling, which you see a lot of today. Most high-speed serial interfaces use differential signaling. If you were to use individual inductors on each of the differential lines, you would end up making yourself a filter, and that filter would round off the edges of the signal. By using a common mode filter, the fluxes of the 2 differential signals cancel each other, and any common mode noise would be attenuated, so it's an advantage. You're using 2 windings on the same core to influence each other and produce a better result, better signal integrity. Dual mode inductors are a special blend of common mode choke and differential inductor. You can clearly see that this is a common mode choke on a squaroid, but it also has a center leg. There's a large gap in that leg, which is used to control the amount of leakage inductance, which provides inductance for differential mode filtering. Clearly there's a compromise of both types, but in some applications it's all you need, and it saves on the number of components. I call this classic coupled inductors because it is probably where the term is used the most, in relation to Chook, SEPIC, or Zeta converters. Professor Chook defines a coupled inductor this way. A coupled inductor is one where if the coupling is removed, the converter must still operate. What he's really saying is related to the topology, that its function is not dependent upon the interaction of the windings on a coupled inductor, but it can benefit from it. The definition I gave earlier is topology independent and applies to all coupled inductors, of which this is a subset. When we think of coupled inductors, it's often to reduce the component count. In the Chook type converters, there's also the advantage of reducing the inductance required or having lower ripple if the inductance remains the same. In these applications, the right amount of coupling is important. With too little, the benefit is not realized, and with too much, causes circulating currents. Controlling leakage can also help steer ripple currents to the input or the output. In the classic Chook converter, which is also similar to the SEPIC and the Zeta, you use the coupled inductor to reduce the inductance that's required, and you can steer the ripple current to the input or the output. It works like this. When the switch closes, currents in the green are flowing so that you are building up the magnetic field in L1. L2, which was previously charged, is now connected to ground, so the current can flow through the switch into C3, the load, and into L2, building up its magnetic field. Note the polarity reversal on the output. When the switch opens, the voltage reverses on L1 and adds to the source to charge C2. This provides for a voltage boost. The voltage reverses on L2 and it delivers its energy through D1 to C3 and the load. Notice the currents in both inductors are flowing in the same direction. In this diagram, I've just swung the inductors up so they share the same core as in an actual coupled inductor. Otherwise, the schematic is exactly the same as before. You can see here that during the on time, the current is flowing down through L1 and it's also flowing through L2 in the same direction. Since the polarity is the same, you're actually adding the fluxes together as indicated by the dots. Because they add together, less inductance is needed to achieve the same ripple, and that's a big advantage. For the same inductance, there is about half the ripple versus using separate inductors because they contribute to each other, but you need to handle twice the DC bias. Here's the SEPIC converter, which looks very similar to the Chook converter, but the position of the diode and the second inductor have been switched. In this case, the principle of operation is the same. The advantage is the output voltage is not inverted, and there is a common ground reference for power supply all the way through the output. This is very convenient to use, especially in battery systems that also use AC power adapters and chargers. Whichever type of power you plug in, everything stays ground referenced. Another type of coupled inductor is the multi-winding output inductor. These are used in multiple output power supplies where there are several outputs but only one is regulated. Even if these additional outputs do not require tight regulation, they can have large voltage swings depending on the loading. By linking all the outputs through the multi-winding inductor, the outputs influence each other and there are reduced voltage swings. Overshoots are reduced because the other outputs absorb or provide energy, which helps to minimize the swing that would normally happen. It also simplifies current limiting because any single secondary short will reflect back to the primary side through the inductor. It's also a little easier to control because loop gain irregularities are eliminated by the dynamic linking of all the outputs through the common mode inductor. A single inductor may be smaller and lower cost. And the other thing that you can do is steer the ripple currents to the highest voltage output. Because capacitors store energy proportional to voltage, remember energy is 1/2 CV squared, you can direct the ripple current to the highest output voltage, and you can actually use smaller capacitors in your power supply. Good reference to these is the app note by Lloyd Dixon. This is just an example of the schematic showing you how we draw the multi-winding inductor. We use the core lines as the joining element. One of the main cautions when you use this type of inductor is that the turns ratio between the individual inductor windings has to be identical to the turns ratio of the transformer outputs. If this is not the case, there would be circulating currents caused by the voltage differential, which would cause increased losses among other problems. The way the current is steered from one winding to the other is by controlling the leakage inductance between the windings. You pick one winding as your reference and then you control the amount of insulation, the space between the windings, which will affect the coupling, and then you can steer ripple. If they're close together, there will be low leakage resulting in tight coupling, the opposite if they're further apart. The order of the windings, their relationship to each other, also plays a role in this. Flyback transformers. By definition, a flyback transformer is an energy storage device, and therefore it's an inductor. This is a big point of confusion because we all call these devices transformers, when what we really have are two separate inductors that use the same core which links them together. Because they're using the same core, they share mutual flux, and because of that, the voltages and currents will have the transformer property of turns ratio. What that means is the voltages and currents are reflected across the input and the output. This is important because the reflected voltage in particular affects the ratings of the semiconductor devices. Also, because the input and the output use different windings, the device has galvanic isolation, which is a transformer property. It's a coupled inductor because the windings are coupled together with transformer-like properties. It's not a transductor, a mashup of transformer and inductor, as some people would like to call it, because a transductor is actually another kind of inductor. The flyback transformer could be called a transformer choke, which is a more accurate term. Basically, it's an isolated version of the buck-boost converter. In a flyback converter, each phase of the power conversion has its own inductor, but they share the same core. In the switch on stage, you use the left side, and in the switch off stage, you use the right side. One winding builds the magnetic field, the other harvests it. It has the transformer property of turns ratio, so voltages here are reflected both ways, meaning you have to take this into account when rating the switches. Here we see it in its isolated state. During the switch on state, the other winding is not being used. The load is supplied from the output capacitor alone. This is like a boost converter. What you have here in reality is a controlled short circuit. As long as there is inductance, you'll have a magnetic field that will limit the rise of current, but at some point you turn it off. When the switch opens, the current wants to continue flowing. The collapsing magnetic field reverses the voltage polarity, which rises until something happens. The energy has to go somewhere. It turns out in a flyback, because the windings are linked by the core, both windings have the same action. The output winding conveniently has this diode oriented such that now that the winding voltage polarity has reversed, it can conduct and current will flow to the output capacitor and load. The stored energy is harvested for the load. Fortunately, we can put different number of turns on each winding, and we can effectively have a turns ratio that allows us to optimize the duty cycle. If the duty cycle was 1:1 and we wanted a large change in voltage, we would have to have a very narrow duty cycle. To reduce 100 volts to 1 volt, you'd have to run this at 1% duty cycle, which is not very practical or efficient. But by using a turns ratio, you can optimize it closer to 50%. This is the reason why flybacks are used for universal input adapters and chargers, which have a wide input voltage range, typically 85 to 375 volts DC. Unlike a transformer, which strictly outputs to the turns ratio, a flyback's coupled inductor actually decouples the output winding from the turns ratio because they operate as independent inductors during their portion of the power cycle. I hope that doesn't add to the confusion, but think it through. Another place that you see coupled inductors referred to are multiple winding inductors used for auxiliary outputs on buck converters. They go by various names, all trademarks of their respective owners. You can see the same thing on power factor inductors that have an auxiliary winding. The extra winding works just like a flyback circuit in the switch off cycle. These outputs usually work at a much lower power than the main inductor using residual energy. You know by now that you cannot use a coupled inductor known as a common mode choke in this application because it's not designed to store energy. All coupled inductors are not created equal. Transductors are AC inductors along with reactors, but with an added twist. As an example, one type of transductor is the magnetic amplifier. These are not used so much today, but in the days of vacuum tubes, before we had high-power silicon switches, They were actually quite common because a small current could be used to control a large current in a load. What you have is a two-winding inductor where one of the windings is a controlled impedance in series with the load. This impedance is variable, controlled by a small DC current in the other winding. You can also regulate voltage by moving this device in and out of saturation. These were often used in servo circuits in the previous century, but in the 90s, they were also common in personal computer power supplies as a secondary regulator. You don't see them as much today, but it's a type of coupled inductor. Here's a little glossary of terms that we commonly use, listed in alphabetical order. Choke, an inductor intended to carry large DC currents. Choke is commonly interchanged with the word inductor. There's no strict rule about its usage. Common mode choke, it's a type of coupled inductor used to limit common mode currents. Coupled inductors are inductors with multiple windings that benefit from some interaction with each other. Current compensated choke, same as a common mode choke. Differential choke, an inductor that can handle DC bias and used in EMI suppression. Flyback transformer, a type of coupled inductor taking advantage of transformer-like properties. Inductor, the generic term that we use for devices that store energy or limit currents. Reactor is just a type of inductor used for AC circuits. Transductor, a variable coupled inductor for AC circuits that uses a DC control winding. Transformer choke is just an old but true reference to a flyback transformer. And transformer is a device that transforms power instantaneously without storing energy. Let's talk about symbols for a moment. There is the IEC 60617-4 standard for symbols for electronic components. These are the symbols for inductors. The first symbol is for any inductor, though I would tend to use it for an air core. The second one would be more of the traditional inductor that we commonly see with a magnetic core where a single line represents the core. The third is intended to show a magnetic core with a gap. It would be your traditional DC type inductor or choke used for filtering. And the fourth one is showing a tap in the inductor winding. Then there is this alternate form, which for me is confusing, but it's actually the preferred way. All the schematics I've looked at in my lifetime have been more traditional, so it's very difficult for me to envision this as an inductor. Here in the IEC 60617-6 standard are symbols for transformers. You can see it's very similar to what we traditionally see on schematics. The main change is that the core, often represented by two lines between the windings, is not included. In the second one, the polarity dots showing the orientation of the windings are on the outside. It's common to see those on the inside of the first loop. In the third diagram, there's a dashed line between the windings, which is the common symbol for a shield within a winding. Not to be confused with a gap core that we saw for inductors on the previous slide. Here there's no core and a dashed line as a screen would normally be connected to something. Lastly, we have the symbol for a tap, and in this case a center tap, which could be anywhere, and that's common. And here is the alternate symbol form. You'll notice that there is no symbol for a coupled inductor. We've come full circle. We started with the only way to know that it's a coupled inductor is from the circuit contacts, and we end up there again. So let's summarize. There's probably no way to untangle this mess of what's called a coupled inductor. But now you're smart enough to know the difference is based more on circuit topology and application than some idea about two windings on a core. You know coupled inductors are not transformers and they're not interchangeable with transformers. Coupled inductors exploit a benefit of several windings being on the same core. Schematic symbols are all about context. These are not the only types of coupled inductors used, but I've shown you the most common ones. Now that you've seen the many ways that coupled inductors can be used, learn to use their unique benefits in your application. This concludes the presentation on coupled inductor confusion. Thanks for watching.